Hi, my name is Adrian Victorio.
I'm Ryan Tran.
I'm Jerry Wright.
And I'm Seonkwan.
We are Group 9, and this is our presentation on gearbox design, where we redesign a gearbox based on a different horsepower.
So looking at gears, we noticed that N2 was equal to N4 and N3 was equal to N5. Finding the gear ratio, which was equal to the output speed divided by the input speed, we were able to find N2 and N4, which we found to be 16 teeth. N3 we found was equal to N5, which was equal to the gear ratio times N2, which was equal to 76 teeth. We checked the output speed, which was 106.37 revolutions per minute. The speed of gears 3 and 4 was found to be 505.26 revolutions per minute. The torque input was equal to the input power divided by the input speed, and after conversions, we came up with 131.3 pound-force per foot. The torque on gear 3 was found by the input torque times the input speed divided by the speed of gear 3, which we found to be 623.69 pound-force per foot. Torque on gear 5 was found to be the input torque times the input speed divided by the speed of gear 5, which we found to be 2,962.5 pound-force per foot. Now looking at the gear specifications, we found the P-min to be approximately 5 teeth per inch. And using that, we found D2, which was equal to D4, to be 3.2 inches. D3 was equal to D5, which was 15.2 inches. The velocity of gears 2 and 3 was 2,010.62 feet per minute. The velocity of gears 4 and 5 was 423.29 feet per minute. The tangential force on gears 2 and 3 was 984.77 pound force. The tangential force on gears 4 and 5 was 4,677.6. At gear 4, and bend, the geometry factor for pitting resistance was found to be 0.1329. The dynamic factor was 1.22, or 2.51, which was rounded to 2.5. The pinion proportional modifier was equal to 0.0718. The mesh alignment factor was equal to 0.166. The load distribution factor was equal to 1.24. And using these values, we found the contact stress to be approximately 188 KSI. The life of gear 4 was found to be 3.64 times 10 to the 8th revolutions. The stress cycle factor was 0.92. The gear contact strength desired, we found to be approximately 245 KSI. The factor of safety we found to be 1.35. The bending stress we found to be 52 KSI. The allowable stress we found to be 67.5 KSI. And using those, we found a safety factor of 1.29.
Moving on to gear 5, we use figures 14.6 to find geometry factor J, and figures 14.14 and 14.15 to find the stress cycle factors. From there, we found that the contact stress is about 187 kpsi and a bending stress of 33 kpsi. From there, we found that the factor of safety from contact stress is 1.39, and the factor of safety due to bending is 2.1. Moving on to gear 2, same methodology. This time we find that the contact stress is 103 kpsi, which gives us a factor of safety due to contact stress to be 1.2. And the stress due to bending was found to be 15 kpsi, giving us a factor of safety due to bending of 2.4. Moving on to gear 3, again, same methodology. We found a contact stress of 103 kpsi and a bending stress of 10 kpsi. From there, we found that the factor of safety due to contact stress is 1.34, and the factor of safety due to bending is 3.18. So overall, we found that gear 2 should be made out of through hardened steel grade 2 with a diameter of 3.2 inches and a face width of 2 inches. Moving on to gear 3, it should be made out of nitrided 83.5 HR15N steel grade 1 with a diameter of 15.2 inches and a face width of 2 inches. Gear 4 should be made out of carburized hardened steel grade 3 with a diameter of 3.2 inches and a face width of 2.5 inches. Gear 5 should also be made out of carburized hardened steel grade 3, but this time with a diameter of 15.2 inches and a face width of 2.5 inches.
So for the shaft design, we decided to go with the 1050 CD steel. The lowest factor of safety was located at where the bearing resides, which is 1.077. For our design process, we first assumed a material, preferably weaker material. In our case, we went with 1020 CD steel. We performed calculations to determine diameter at a critical point, and we also made sure to check all the critical points with that throughout the shaft. And if the material is not strong enough, we will select a stronger material and continue the iteration until we find a material that can sufficiently withhold the stress that are applied in the shaft. So for our W tangential of 2.3, we got 984.77 pound force. For tangential of 4.5, we got 4,677.66. Our radial for 2.3, we got 358.43. And radial for 4.5, we got 1,702.53 pound force. And on the bottom right corner, you can see our drawing for our SolidWorks model that we did for our shaft. Next slide. So for our bearing selections, our C10 value for point A came out to be 29 kilonewtons, and for point B came out to be 49 kilonewtons. Our bore diameter came out to be 1.75 inches. So we first wanted to go with a ball bearing. However, for our bore diameter, which is roughly 45 millimeters, the C10 values were a lot lower than our C10 values. So we decided to go with 03 series cylindrical roller bearing, a bore diameter of 45 millimeters, which has a C10 value of 72.1 kilonewtons, which is way over 29 and 49 kilonewtons. The slope was found to be 0.0005 radians, which is well below our max level, which is 0.0008 to 0.0012 radians. For our key design, the material we selected was 1020 CD steel. Our design criteria was to have factor of safety of 2, and width was 0.5 inches. And using these information, we were able to find our length, which came out to be 0.988 inches, which is roughly about 1 inch.
This is our deflection analysis that we did on FEMAP. The shaft here is a simplified version of the drawing we showed on the previous slide with the same lengths and diameters. To make the model, the ends of the shaft were pinned. Also, the material properties were defined as steel with a Young's modulus of 30 mpsi and a Poisson's ratio of 0.292. The tangential and radial bearing loads are applied on the shaft as loads. As you can see, our max deflection is less than 0.002 of an inch, which is reasonable. Looking at the model, the red area is where there is maximum deflection. We use this maximum deflection and its distance from the end of the shaft to obtain a worst-case scenario for slope by making a right triangle. As mentioned earlier, this slope is safely under the max slopes listed for a cylindrical ball bearing. And that is it. Thank you for listening to our presentation.